Evening, everybody. 5 o'clock Thursday night. Time for Calc 3. So I was looking at the schedule today. After today, we actually only got 3 weeks of new material left, so we're really getting down to the nitty gritty. Yeah, I noticed that too, Daniel. I'm not sure why. I haven't really heard from too many people. One person got their injection today and feeling a little under the weather. We might get some more people as we in the first few minutes here, but that's okay. We press on. So like I said, after today we have 3 weeks of content left. Today we're going to get introduced to line integrals, which you saw in the video lesson. So I'm going to talk a little bit about line integrals. We'll do a couple examples together and then have you guys try some. And then next week, we're actually going to continue with line integrals. We're going to look at a couple of theorems on how to solve line integrals. Actually, I think line integrals is actually a pretty cool topic. It's to me, one of the funner things that we do in Calc 3 because of all the different ways to solve them. And, once we get those theorems next week, there are going to be problems that you, depending on the way you want to approach it, you can actually do it one of 3 different ways. I hope so. Let's do this. So I don't want to worry about next week right now. Let's focus on the concept of line integrals and how to solve them in general. So first off, in Calc 1, we learned how to integrate a function along the x-axis, right? And we talked about it in Calc 1. So this is just kind of a review. In Calc 1, when we would do the integral from a to b, that integral would give us the area under the curve. All right. Now, what's happening is we have a surface in 3 space, and there's a curve going through the surface. And what the line integral gives us is the area under that curve. And I have let me show you a picture because it's just unfortunately, it's too hard for me to draw. I had a website where I thought the picture was kind of nice. And then you guys can tell me what you think. All right, so this is from this whitman.edu. It has some nice information on there. But this picture on the left is talking about what's going on with a line integral. Whoops. Right here. So what this would be our surface, the blue, and we've got a path through our surface. What the line integral gives us is the area under this curve right here and above the xy plane. So this green, yellow, red, purple, that's the area under this curve. So what a line integral essentially is doing is the same thing that our integral did in Calc 1, except now we're not confined to the xy plane, we're actually in 3 space. So it's still doing the area under a curve, but now that curve can be any kind of line in 3 space. All right. So if I kind of turn this picture around, you see how this colored area is the area under this curve in 3 space. That's what a line integral of a function gives us. All right. So I like this image here. I think that it does kind of a nice job. And like I said, it's not something I can draw. Here's the website I pulled that from in chat. Now, that's not the most useful aspect of a line integral. And actually, we're not going to focus on that too much. But that's just in general what it does. So it functions very much like our integral in Calc 1. And in fact, as you saw in the videos, the integrals we're going to be doing today are all single variable integrals. Okay. What happens is we parameterize the curve and we integrate with respect to our parameter variable. And guys, if you have questions as we go through this, feel free to stop me. As of right now, we got a small class, so let's take advantage of it. That's what a line integral, in general gives us. Now, what does a line integral look like? Well, first off, if we have some, line integral of some function f of x, y along C, where C is that path, C is that curve. So let me bring our drawing back over. C would give this curve right here. Let's see if I'm going to try and trace it. I don't know how this is going to come out. That curve, came out okay. That's C. That's the curve in 3 space. And then we've got some function that we're integrating over, which may not even necessarily be this plane. All right, that plane is just there to kind of help us see the curve. So we got some curve in 3 space, and we want to integrate over it. And this is the formula, because let's talk about why this formula works. Not that you have to memorize that, we just need to know how to use it. But basically what happens is we're integrating over the function. So that's what's going on here. This is just our function, but we're putting in our parameterization for x and y, okay? And I'll show you what that looks like in an example. This part here is what makes it that integration over the curve. Because what's happening is r of t makes the curve. That's our position function. So maybe I should just leave this over here. That r of t is making this curve right here. Well, then think about what r prime of t dt does. R prime gives us the tangent to that curve, and then dt is moving in the direction of increasing t. So this r prime of t dt moves us along the curve. So what we're doing is we're integrating this function as we move along the curve. Now, because what we're doing is the magnitude of r prime of t dt, well, this is the magnitude of a vector, right? This is something from way back in module 1, the square root of the sum of the squares of the components. That's all that's going on here. So that's what makes up the line integral. Now, a couple things I want to point out. Now, first off, if the function is 1, so if I were to just do this and say, okay, let's ignore that for just a second, that integral that's left, that's arc length. We did that earlier this semester. So basically what we're doing is we're integrating over the length of the curve, and that's where we're integrating this function over the length of the curve. So that's what's happening mechanically. So if this function is a density, for example, then what we're getting from the integral would be the mass of the curve. So if you can remember back to, we can do these in 3 space too. If you remember back to when we did space curves, we did the spiral, we had the slinky. Well, if we use the parameterization of this slinky, and this function here is the density of this slinky, this integral would give us the total mass of the slinky. All right. Now, that's not obviously the most important thing of a line integral, but I just want to give you something that you can kind of sink your teeth into, something that we get a feel for. All right. So that's a line integral of a function. And that's what it does. So let's look at an example of what this looks like. And like I said, guys, if you have any questions, feel free to ask. We're going to do one from the worksheet. So let me bring that over. I'm going to do number 1, and I'm just going to bring it over here just so I can write down the problem. We're going to do 1A. You guys are going to do 1B. So 1A, first off, we have the function is 2x plus y, and our curve, our path, is given by the position vector 3t plus 2, 5 minus 4t. And t is going from 0 to 2. All right. Now we're gonna work through this one, and I want you to see how this formula plays out. Remember what this is here. This is x of t. This is y of t. All right. Well, we know we need x prime of t and y prime of t. So basically what we're going to do is find the derivative of r prime. I probably should have put a t in there, but we won't worry about that right now. We're going to do the derivatives of each of these with respect to t. So 3 comma negative 4. So that's our r prime of t. The other thing we have to do is we have to get our function in terms of t. Well, what we're doing, remember, this is x, this is y, so this is getting plugged in for our x's, this is getting plugged in for our y's. So what f of x of t will look, y of t will look like is, and guys, when you go to do this in homework or on your own, you don't have to do all these steps. You can do all this stuff at once. I just really want you to see where everything's coming from. So 3t plus 2 plus 5 minus 4t. We'll simplify that. So we've got 6t, that's a bad arrow, plus 4. And there's nothing to distribute here, plus 5 minus 4t. And we'll simplify that down to what? 2t plus 9. All right, so that is our function in terms of t, because we want everything to be in terms of t so we can integrate. So our line integral, let's just call it L, is going to be the integral of our function in terms of t, which is 2t plus 9. And then we do the square root of the sum of the squares of r prime of t, the derivative, this guy here. So square root of 3 squared plus negative 4 squared. This is all in terms of t. And this, the range on your parameter, is the limits of your integral. Now, that's it for setting it up. Now, depending on what our position vector is and our function, these could get messy as far as integrals, but I think setting it up isn't too bad. This one actually simplifies pretty nice. I'm only going to simplify it. I'm not going to go ahead and solve it just for time's sake, because it's a pretty basic integral once we get done, because right here you end up with rad 25, which is just 5, which we can actually pull out of the integral. So 0 to 2 of 2t plus 9 dt. And again, we get back to a single variable integral that, we could have done it back in Calc 1. The rad 25 I pulled out front as a 5, just for a note there. Questions about that? Now, again, if this, let's just say this was a density function, then what this would give us is the total mass along this curve between 0 and 2. Maybe this is a wire. Seems straightforward for now. Okay, well, hopefully that continues. So That is the line integral. Well, good. I'm glad it helped. Guys, that's the line integral of a function. All right. Because there's going to be two different things going on. And I want to make sure we differentiate between the two. So this is the line integral of a function on a curve in 3 space. Now we're going to move on to a slightly different topic. It's still a line integral, but now we're going to talk about a line integral over a vector field. All right. And things are going to change slightly, but not majorly. And I'll talk about that. Okay. So, and when you guys are working on problems, I'll send out the whiteboards so that you guys can use those as you go through. All right. You remember our Gulf Stream from last time? You know, we had that Gulf Stream for the vector field. Well, depending on which direction we're heading, we may be going with the current, against it, or at some angle with or against it. So when we do a line integral over a vector field, that determines to what extent our path is in the direction of the vector field or against it. So, you know, this is, you know, you saw in the videos that this can be used to calculate the work done by a vector field as we move along a path through a vector field. Now, I do want to emphasize this is for a vector field. So let's make sure we differentiate. The example we just did was a function. Okay, we did a function, we did a line integral of a function over a curve or a path. Now we're going to be looking at a line integral over a vector field, and that's why we want to make sure we pay attention to the notation. All right. Now, we do have to talk about oriented curves, because obviously if we're trying to figure out how much the vector field goes with or against our path, the direction we're going along that path matters. So an oriented path is a path that has a direction. Was not really a big deal in the last problem, because in the last problem, we're just accumulating density, for instance. Now we're actually looking at the work done by the vector field. The vector field's got a direction, as we saw last class. And so now we care about what direction not only do we care about the path, but what direction we're going. Okay. So let's talk about how this works and I'm going to talk to you a little bit about where the formula comes from. And I'm going to try and give it to you in a way that I think is easy. You guys can let me know, you know, if it helps, or if we need more clarification, we can talk about that. All right. So remember, we talked about the notation of a vector field. It's the capital F and it's got a hat. This is important because, as you saw in the other example, just to kind of scroll back, we were actually given a function f of xy. Now we're going to be doing it over a vector field. A lot of times in notation, we use a capital F and some kind of hat on top to show that it's a vector. It will also be in vector notation, all right? And I'll point that out when we do an example. So what happens, the way that we do this is we break that curve, that oriented curve, into a bunch of little straight line segments, so we can assume that the vector field is approximately constant. This is just, guys, I'm just giving you a little background from where the formula comes from. This isn't something you need to memorize. I just want the formula to feel a little more intuitive for you. So what we do is we find the value of our vector field on each of these little line segments. Now, so what we want is we want the vector projection of the vector field in the direction of our path. So what we do is on each little line segment, we do the dot product. If you can remember back, it's been a while, the dot product does vector projection because we want the components of F that are in the direction of motion. If they're perpendicular, then it's 0. So that's where this comes from. Dotting the vector field with our position vector. Now, what we do is we sum up all those pieces, we get a Riemann sum, and then we take the limit as n goes to infinity, and that's where this formula that you saw in the video comes from. This is what we're going to focus on from here on out. And I will talk a little bit about the differential form, but I pretty much do them all as dot products because to me, that's the easiest way to set them up. And I'll show you what I mean. So here's our formula for line integral. Everything comes from this. F is a vector field, and C is our path. And dr is going to come from the parameterization of our path. So if the vector field is a force field, then what we're calculating with this integral is the amount of work done. And that's the same work from Calc 2, the physics definition of work that the vector field does as an object moves along C. So we could calculate the work done by a gravitational field because that's a force field by doing these line integrals. Now, since the line integral uses the dot product, if the component's in the same direction, it's positive, negative if they're in opposite directions, and 0 if they're perpendicular. Well, think about what we want. We're trying to find out what extent our path is in the direction of the vector field. So this dot product works perfectly for us because we want it to be positive if they're in the same direction, negative if we're going against the vector field, and 0 if they're perpendicular. Now, here's the differential notation. Like I said, I don't use this very often, but because it was in the videos, I do like to bring it up. You know, so our dr is dx dy, and we can think of our vector field as being made up of components that are functions of x and y. So then doing the dot product gives us p of xy dx plus q of xy dy. This is that differential form that was in the last video in the lesson. You don't need it to be able to do it. And there's issues that you can run into, especially if you're not parameterized, because if p of xy is both in terms of x and y, we can't integrate with respect to x. Similarly here, we can't integrate with respect to y if q is in terms of xy. If they're constants, or if p is only in terms of x and q is only in terms of y, this works out perfectly. It'll also work via parameterization, but if you're going to parameterize, we're just going to stick with the dot product, all right? Pretty much everyone we do in here, you can do with the dot product, but I just wanted to make sure I mention this notation, and it's similar in 3 space, all right? Okay. So I want to focus on how to evaluate line integrals of a vector field. So we want to evaluate this guy. What does this mean? What does this look like? Well, here's what's happening. If we have a curve in 2 space and it is given by x of t, y of t, then that dr, this piece right here, is r prime of t dt. R prime of t is just the derivative of r. In 3 space, we just add on that third component. All right. Now, let's take a look at what this looks like. And like I said, this is how I'm going to set it up. I'm going to set it up and then do the dot product within the integral. You can tell me after I do an example what you think. Excuse me. All right. So let's take a look at this. And I'll show you how I like doing this. You guys can tell me what you think. All right. So first off, we've got a vector field. So let's write that down. So our vector field. And you'll get a chance to try one of these today too. And hopefully you'll feel better about it before the end of class today. All right. So that's our vector field. Here's our curve. C is the parabola, y equals x squared, between 0, 0 to 2, 4. So what we're going to need is a parameterization of this in order to work this problem. So as you guys start to work problems, one of two things is going to happen. Either you'll be given the parameterization, or you're going to be parameterizing something that you can handle, something like this, which I'll show you in a second, or part of a circle. Remember that to do a circle, it's just our trig functions, cosine of t and sine of t. And then to change the radius, we just multiply it by something. So you guys will get some practice. In fact, we might do a parameterization together of a circle, just so we can see what that looks like. Okay. So let's talk about parameterizing this guy, and then I'll let you, and then you can see how this stuff works. So the first thing I would recommend doing is write down the formula, f dot dr. All right, now let's talk about what each of these are. F is the vector field. Dr is going to be our parameterization. So I first need a parameterization of this guy. Whenever you're given a function, the easiest way to parameterize it is to let x equal t, and then let y equal t squared. And t is going to go from 0 to 2. It's a nice little trick that will take any function and parameterize it, because really all we're doing is substituting t for x. Why 0 to 2? Well, because x is going from 0 to 2, and since y is t squared, y is going to go from 0 to 4.
Why not just leave x how it is and not do
that? What do you mean leave x how it is?
Like we make a substitution for t, but like what's the point of making a substitution for t?
Oh, you mean leave it in terms of x?
Yeah.
We'd run into issues here because we're going to have to plug in our parameterization for these x's and y's. If we leave x as x, we could, Cooper, we could make y equal to x squared, and it would do the exact same thing. This is just a more general process to introduce a third parameter.
Okay.
So we could in some cases, but in other, depending on the parameterization, we may not always be able to. What we're doing here will always work. But you're right. If all we're doing is changing a function, we don't have
so when it's more complicated, we'll need to use a t.
Yes.
Okay, that's fine then. Totally.
Yeah.
All right. That's
what
I mean. That's the best answer. To be honest with you.
Yeah. The reason this would work is because we do have a function. If we have something that's not a function, then we have to parameterize in terms of the third variable.
All right.
So basically, our r of t is t squared. All right. That makes, now remember, going from right here, this here is f in terms of t. This here is the dr. So just as a reminder, let's put a little note here. That dr, that is r prime of t dt. So we'll find r prime of t, which is 1, 2t. And we need to get f in terms of t. So that means we take our parameterization and we sub in. So these x's will become t. The y's will become t squared. So negative t squared sine of t, cosine of t. And I want you to see and because we're doing the derivative here, I like to put a dt on there. All right, because basically what it is dr dt. So here's what happens. Taking this integral over c from f dot dr, show you what the dot product looks like in here. So negative t squared sine of t, cosine of t, and of course that's right in the way. And I'm going to just get rid of our note. Sorry about that. Put it right in the way. All right. That's getting dotted with our dr, which is this piece right here. 2t dt. Okay. Now, once again, just like with the previous problem, our limits are just from our parameterization, so 0 to 2. I want to pause there before I go to the next step. Any questions about how I got this integral set up? I'm trying to break it down into steps because these steps are always the same. If you're not given a parameterization, you create your parameterization. You find the derivative of your parameterization. You plug your parameterization into the vector field, and then you dot those together inside your integrand. Those are the steps. Now, I know it's been a while since, because this is the easiest parameterization. So the question came up, why does x equal t? This is the easiest parameterization of y equals x squared, is to say, okay, I'm going to let x equal t, and then y is going to equal t squared. And that gives us a parameterization of this parabola so that we can write it up as a position vector in terms of one variable. Now, this is the parameterization you use if you have a function. In other words, if you're given y equals something that's a function, this will always work. Let x equal t, and then let y equal the function, replacing the x with the t. But we need a parameterization of our curve for this, to do line integrals this way. Other questions about how we got to here, or more clarification on that? Again, in some problems, you'll be given a parameterization. So you skip right to finding r prime of t, plugging r of t into the vector field, and then calculating your integrand. So we do the dot product, which is this component times this component. So negative t squared sine of t times 1, and then plus cosine of t times, let's use parentheses again, times 2t dt. And again, limits are 0 to 2. Now, let's talk a little bit about going from here on out. So negative t squared sine of t plus 2t cosine of t dt. What we would do here to solve this by hand is we would split this into two integrals. We do 0 to t of negative t squared sine of t dt plus the integral from 0 to 2 of 2t cosine of t dt. And both these integrals would be done with integration by parts. I'm not going to do that because it'll just use up too much class time. But again, integration by parts, it would take 2 times of integration by parts to do this first one and just 1 time for the second. So it's really not that bad, but I realize you guys may not have done integration by parts in a while. There's a good chance it'll show up again in this section. So just be aware. Now for this one, I went ahead and did it in Symbolab because there's something I want to show you. All right, so there's our integral, and it comes out to be negative. Now, what that means is that over this path from 0 to 2, we're going more against the vector field than with it. And that's why we're getting a negative answer. So let's see what this looks like and make sense of it. This is in Calc Plot 3D. Last time we saw how to add a vector field, and I'm just constraining it to the XY plane. Then to add the parameterization, you'd add a space curve. And since we're only in 2D, we're going to let the Z component be 0. So there's our path. And we can even animate it, and you can see the point going along. In case you're wondering what those arrows, those vectors are, that's the tangent vector in black, or the velocity vector. This is the acceleration vector in green, and this is just the position vector here in blue. If you find those distracting, you can turn them off. All right. But so that black dot, that's our particle going through this vector field. And we can see right there, the vector field's perpendicular. So it's having no influence on our particle as it goes along its path. But as we get up here, look at that spot right there. Now we're kind of starting to go against the vector field. And we see that the magnitude of the vectors is getting larger. So it makes sense that we're getting a negative answer, but a small negative answer. All right, so we can actually get a visual of what's going on. Questions at this point? About how we set up the integral. Like I said, I didn't do the solving only because of time. I want you guys to have time to try some of these. And same with when you guys are working in groups. Once you set up the integral, feel free to use Symbolab or Wolfram Alpha to calculate it, because I don't want you to spend a lot of time on that. But I want you to, but if you got any questions, hopefully that helped with the setup of a line integral over a vector field. Questions at this point? Okay. Then there's 2 more things I want to do. Number 1, I'm going to bring the worksheet back over because there's something I want to show you. Remember, I said earlier, we really want to make the distinction of whether we're doing a line integral over a function or over a vector field. Notice number 1, we're doing the line integral over functions, f of x, y equals. So notice the notation there, right? Number 2 is where we're doing line integrals over vector fields. Notice that now we're given something as a vector instead of a function. So I wanted you to see the difference there. And I'm going to have you try a couple of these here in just a minute. And actually, let me go ahead and put this in chat in case you don't already have it. So there's the worksheet. One of the ones I'm going to have you do is 2D, but I want to go through the parameterization with you. The right-hand side of the unit circle in a counterclockwise direction. So I want to show you. So first off, let's go through how we could do this one graphically. So let's clear our thing here. And when it says unit circle, the radius is 1, but I'll talk about how we can change for different radii too. So the way you would do this, if you guys want to plot them in the plotter, you're going to put in your vector field. So our vector field is y, negative x, 0, because we're just going to be in 2D and we're going to restrict the view to 2D. So there's our vector field. Now, if we're moving counterclockwise, we can already see we're kind of going with the vector field. So we're going to expect our answer to 2D to be positive. Let's talk about the parameterization for the right-hand side of a unit circle. Whenever you're parameterizing a circle, you're going to be using cosine and sine, all right? But I want to show you a couple things. So we're going to put that in. We're going to put it in as a space curve. And let's just go with our regular x is cosine and y is sine. And again, put 0 in it if you're only in 2D. All right, and for right now, let's put in the whole thing. All right, so there's our circle. And if you're wondering which direction you're going, just use the animate. So we're going counterclockwise. If I wanted to go clockwise, so if we wanted to go this way, there's a couple different ways to do it. And this is where it's going to take a little bit of playing around. And that's why I'm showing you this. If you want to go the other direction, because remember with these direction matters, there's a bunch of different ways to do it. You could go from 2 pi to 0, or switching the trig functions. It makes the same graph, but look at what happens when I animate. I'm going the opposite direction. So if I only wanted, let's just say we wanted the right-hand side clockwise. There, going from 0 to pi. And then I can check my direction with the animate. So this is something you can use to help you as you get used to doing your parameterizations. We're going clockwise on the right half of the unit circle. If you want to increase the radius, let's say our path is a circle of radius 2. Just put that out in front, and there's your circle of radius 2, still clockwise. Okay. Now let's go back to the one we're trying to create. So I'm going to give you the parameterization for this one. You'll get practice in the homework of doing the circle, and you'll get good at it. I promise you. I'm not even worried about that. All right. Now, we're trying to come up with the parameterization of the right-hand side of the unit circle going in the counterclockwise direction. So we've got the direction right. We just don't have the right part of the circle. We want to go from here to here. So we need to, there's a couple options. I mean, you can change the trig functions. You can change signs on the trig functions. Guys, when I tell you there's an infinite amount of ways to do this, there's literally an infinite amount of ways to parameterize this. I'm just showing you a couple of the more obvious ones. The easiest way to change this for the left-hand side is to leave the trig functions, but go from negative pi over 2 to pi over 2. Now we're on the right-hand side and we're counterclockwise. So this would be the parameterization you want to use for 2D. X is cosine, y is sine, and your t is going to go from negative pi over 2 to pi over 2. Remember, this part here is important because those are going to be the limits on your definite integral. Now, I'm going to let you guys try the rest of it based off of the steps that we talked about earlier, but I wanted to go through the parameterization of a circle just to give you a little bit of practice with it. But even if we look at the worksheet, notice for 3 and 4, you're given the parameterization of the path. So you're only going to be expected to come up with the parameterization in very simple cases. If it's given as a function, like the example we did earlier, or if it's part of a circle. And that goes, and I'm talking for the final exam as well. I won't ask you for anything more difficult than either a circle or something given as a function. Anything more difficult would be given, all right? Okay. Questions at this point? So what I'm going to have you guys do in groups is 1B, 2D, and I'll put this in chat as well, and 4. Now, here's the thing I want you to take away. We didn't do 1 in 3 space yet, but the steps are the same. You've got your parameterization, so you find R prime of t. You plug R of t, so that's x, y, and z, in for your x, y's, and z's here. You do the dot product, and you do it actually not a bad integral. And there's your limits. I know we didn't do 1 in 3 space, but I think you guys can do it based off of the steps we did earlier. But before we break up into groups, any questions? So these are going to be the 3 problems that you can post in the forum. These are the ones I want you to try. As always, the answers are on the second sheet.
That was privately to me. You just sent that to me privately.
Oh, thanks, Cooper.
Yep.
Sorry, guys. I put this in chat and accidentally sent it just to one person. Remember, you don't have to worry about solve. None of these integrals are actually that hard to solve by hand. So if you want to solve them in your groups by hand, go ahead. But if you want to use Symbolab, that's fine too, because I want you focused on the setup, not the solving, because they're all single variable integrals. And the integration in them is actually not that bad. All right, then let's get you guys into let's get you guys into groups so that you guys can try some. And as always, feel free to ask me questions. Okay, should have an invite to a room now. And guys, like I said, try these. Let me know if you have questions. I think we have enough time that you can get through all 3 of these. I just want you guys to see what it looks like in 3D, guys. It's not anything different. So for number 4, we've got the vector field, z, 2y, and x. This might take us over 6:30, so sorry for that. And this time we're given the parameterization. It's like I said, in some of these cases, you'll be given the parameterization. Only if it's like a circle or given as a function will you guys be finding it. And you guys will get good at that really quick. But I want you to see that this is actually the same steps. We probably won't solve this integral, but we'll set it up. So 2 things we do first, and it's up to you the order. First thing, I like to find the R prime of t because it's right here, which is just the derivative component by component, 1, 4, 2t. And then we want to get f in terms of t. So z is equal to t squared. Y is equal to 4t. So that's 2 times 4t. And x is equal to t. So let's just simplify that a step. 2 squared, 8t, t. So what that is our vector field using our parameterization. Now we do our f dot dr, which is going to be our vector field in terms of t, dotted with 1, 4, 2t, dt, and t, our limits are 1 to 2. And now we just do the dot product. So we got 1 to 2. T squared times 1. So let me write it all out. So plus 8t times 4. And plus t times 2t. dt. Probably a couple steps of simplifying we're going to want to do before we do the antiderivative. So t squared plus 32t plus 2t squared dt. We'll combine those t squared terms. So 3t squared plus 32t, that's not a t, sorry, going too fast. 32t dt. All right, and now we're back into Calc 1. Antiderivative of this, plug in our limits with the fundamental theorem, and we get our value. I know I went through that one kind of quick, but I wanted you to see that in 3D, the steps are still the same. Take your parameterization, find its derivative, plug in your parameterization into the vector field, dot the two together, and then you have your integral. Questions about that? How are we feeling about line integrals now? I remember we had two different things going on, right? We had line integrals of a function, that would be like number 1 here. And line integrals over a vector field would be like number 2. Yeah, I would agree with you, Daniel. I think line integrals are a little bit easier than triple integrals. Triple integrals are difficult. I think it's one of the toughest things we do all semester. I do think line integrals are a little bit easier. It's going to take a little bit of getting used to. Only about 10 times easier. I'm not sure how we quantify that, but I'm not going to argue against it. But hopefully this makes you feel a little bit better about what you saw in the video lessons today. Where we're heading next week is we're still going to be dealing with line integrals. We're going to be looking at new ways to calculate them. And actually, we're going to be doing the fundamental theorem of line integrals on Tuesday. You're going to learn about, we're going to get back into conservative and non-conservative vector fields. Guys, it turns out when we can use the fundamental theorem of line integrals, to me, these get even easier to do. Now, we can't always use it. We'll talk about that on Tuesday. But next week, we're going to spend time looking at a couple of theorems, the fundamental theorem of line integrals, and then Thursday's Green's theorem, which are other ways of solving line integrals that are sometimes easier than doing the parameterization. All right. All right. Questions at this point?